We present Generative Latent Textured Objects, GeLaTO, a novel representation for category-level object modeling. In this work, we are interested in reconstructing the appearance of real-world objects with complex geometry and materials, such as these eyeglasses frames, using few input views. In particular, giving a set of input images of an object, like 3 in this case, we seek a representation that can render views of the object from any viewpoint. We are inspired by proxy geometry, like billboard clouds, commonly used in computer graphics, and the recent work of deferred neural rendering, which shows how low-poly geometric proxies, combined with neural textures, can synthesize high-quality novel views of the scene in real time. To synthesize a novel view of eyeglasses, like the one on the right, our representation, Generative Latent Textured Objects, GeLaTO, uses 4 components. First, a set of coarse 3D geometric proxies, which for eyeglasses frames can be 3 planar billboards aligned to the front, left, and right plane of the eyeglasses. Second, a corresponding set of neural textures that encode view-dependent effects like specular reflections and off-surface geometry. Third, a real-time neural renderer that generates output, color, and alpha views. And finally, a generative model of proxy neural textures that provide a category prior for reconstruction. More specifically, we render the proxies into the target viewpoint with the neural textures, together with depth and normal metadata, and feed them to the neural renderer. We can then change the proxy pose and generate novel views. Compared to deferred neural rendering, we do not composite the different proxies with each other, and instead stack them into a deep buffer. This enables the neural renderer to see through the different proxies, and enables better modeling of thin structures with overcomplete proxies. Our representation is not limited to planar proxies. It only requires the proxy geometry to have a consistent UV parametrization for the category. We can, for instance, model cars using freeform patches generated by AtlasNet, which exhibit considerable semantic consistency in the way they cover the object categories. To evaluate our model, we collect a dataset of images of eyeglasses frames. We use a robot to capture 576 images of 85 eyeglasses frames. For each pose, we capture 4 images using 2 conditions, with and without the eyeglasses and with and without a backlight. We perform difference matting against the reference in the lit pair and extract semi-transparent alpha channels. We finally use the unlit image to extract the color channels. Our alpha mats are high quality, yet still contain ghost artifacts due to shadows in the capture. Although these artifacts appear in our novel view synthesis results, improving the mats is not the focus of this work. Novel views synthesized by GeLaTO recreate thin structures, transparent materials, and specular reflections. Here are some more examples. Here, these transparent acrylic eyeglasses frames are captured mostly by reproducing the specularities on them. We evaluate the quality of our category model by visualizing instance interpolations, where we smoothly interpolate the texture latent code. The interpolations between different instances are smooth, showcasing that the latent space of the category is meaningful. We compare our category model with a baseline that uses a VAE. The interpolations from the VAE tend to be less visually monotonic. The category-level model can be used to perform a few-shot reconstruction of an unseen instance. Given few input views, in this case 3, together with the proxy geometry and pose, we reconstruct the instance by fine-tuning into the representation, including the neural renderer, the neural textures, and the latent code. We leave optimizing the proxy geometry or pose for future work. Here are some results of our few-shot reconstruction. We perform a quantitative analysis of our representation compared to the VAE baseline and deferred neural rendering. Our representation is marginally better compared to deferred neural rendering in view interpolation, but the results are significantly better for few-shot reconstruction using 3 input views, as our stack representation enables seeing parts that could be occluded by the proxies. Next, we evaluate the performance of our reconstruction method with respect to the number of views. As expected, using more views leads to better reconstructions. Compared to training our model from scratch on the input, our category model is able to perform better with 3 times fewer views. We also compare to volumetric neural rendering approaches like the concurrent work of neural radiance fields, NERF. Our category level model is better than NERF with 3 and 10 input views. However, with more views, the increased representation power of the volumetric approach of NERF enables it to generate more accurate reconstructions. Note, however, that our model can render null views at real time at 60 Hz, whereas NERF takes several seconds to render a single frame. In addition, fine-tuning our category model takes minutes compared to the hours it takes to train a NERF. We also studied the effect of which parts of the network to fine-tune. We found that fine-tuning the whole network works better compared to only fine-tuning the neural texture, and that optimizing an intermediate latent code of 512 dimensions performed better than optimizing the 8-dimensional latent code directly. As mentioned before, GeLaTO can be applied to objects with more complex geometric variations, like ShapeNet cars, by using AtlasNet patches as the proxy geometry. When performing novel view synthesis, our representation preserves high-frequency details like the number decal on the bottom car. We can also interpolate between different car instances. These are possible thanks to the semantic consistency of the AtlasNet patches. Because GeLaTO can run at real time, we contemplate fun applications, such as virtual try-on, where a user can try out new pairs of eyeglasses live. Given a video stream of a user, we estimate their face 3D pose, fit the proxies to their 3D pose, and composite the GeLaTO rendering on the live view. Moreover, we can also show to the user interpolations of eyeglasses while wearing them. Thank you for watching. Please see more details in the paper and the supplementary material available on the website.